Hello, I'm Phi Myers at PEMY Consulting. Yesterday and today I gave 3 modules as part of the NACE, National Association of Corrosion Engineers, short courses, so I am making these talks available to you on my website. The first module is all about the basics of tanks and the corrosion environments that they're subjected to. The second module relates to how API 653 handles tank corrosion and its issues. Finally, the third module is on how corrosion modeling relevant for tanks had to be done and how it could be implemented if only we had a good minimum data set. Today we are talking about vertical cylindrical storage tanks used in the petroleum industry. These tanks range from 15 to over 350 feet in diameter and store all kinds of petroleum liquids, from fuels to chemicals to crude oil to other petroleum products. Most of these tanks are built to API 650. API 650 operates up to a small atmospheric pressure measured in inches of water column, but when referencing API 650 Annex F, pressures can be increased up to 2.5 psig. When pressures are needed in excess of 2.5 psi, then API 620 is the standard that's relevant, and it can go up to as high as 15 psig. Beyond this, ASME pressure vessels are used. Although I focus on typical API tanks, the ideas apply to tanks built to other standards such as UL and STI. Almost all of these constructions are steel, but one can build tanks of aluminum, stainless steel, or other alloys, and even of non-metallic materials. Today we'll focus on steel tanks. The temperature range varies from cryogenic for 620 tanks to ambient temperatures and temperatures up to 500 degrees F for API 650 tanks. Here's a little diagram that shows the temperature pressure limits for API 650. It's mostly very low pressures, 1 to 3 inches roughly. Above that you would use Annex F in API 650, and as I said, the upper limit is 2.5 psig. All API 650 tanks are good to 200 degrees F, but when you want to go above that you have to invoke Annex M. The universe of tanks is vast. In fact, it's so vast that I have to exclude some things that we are not talking about today. Obviously, fuel tanks for automobiles, plastic containers for gasoline and jet fuel, aircraft fuel tanks, polyethylene tanks, elevated tanks, horizontal tanks, concrete tanks, process tanks. Another form of a process tank, a sewage digester tank. The special shape is for the purpose of circulating the liquids. As the bacteria react with the waste, it generates heat, so it's a reactor of sorts. Solids handling, grain tanks and bins and hoppers. Horizontal tanks, totes, and caged or externally framed tanks. Bag type tanks. Grain storage tanks, propane DOT cylinders, water heaters, and certainly not residential tanks. Wooden tanks, water heaters, potable water municipal supply tanks, and DOT transportation tanks, as well as spheres and chemical processing tanks, usually made of stainless steel or other high alloy tanks. Frac tanks, LNG tanks. What we are talking about is flat bottom vertical cylindrical petroleum storage tanks. Most tanks are 48 feet, let's say 50 feet tall, so you can tell that this has a diameter of also about 50 feet. This shows an important issue. Many fuel tanks are covered or coated with linings and coatings to prevent the water that's sitting at the bottom of these tanks from causing excessive corrosion. There's always water dropping out of almost every petroleum storage tank because of the solubility of water in the organic liquid. Yes, it's soluble just like water vapor is soluble in the air, and if the conditions change, it will drop out and create a fog or a cloud and rain. The same thing happens in petroleum liquids. Here is a pontoon used for a floating suction, and there's a different environment. Inside this pontoon is air, and so if you were to get a leak, the buoyancy of this pontoon would change, and there are many of these types of devices sitting at the bottoms of tanks because corrosion holes have penetrated through them. So this just illustrates one of the many environments that a tank is subject to in terms of corrosion. Here's a bolted tank that's used in the upstream industry. This is more like a typical petroleum storage terminal. These are aluminum domes, and I want to point out that they have exactly the same function as these cone roof tanks. The purpose is to keep out the weather, the rain, the dirt, and so forth. It costs more to build these tanks, whereas open top tanks are shown here, and the floating roof just goes up and down. So the secondary containment, you can see these looks like ponded areas that would contain the release, a catastrophic release from these tanks. They all have them, and that's required per EPA requirements. But it also means that water can accumulate if careful drainage is not done, and that will accelerate the potential for corrosion. So even though I said flat bottom tanks, they're not really flat. There's three basic designs: cone up, cone down, and single slope. This schematically shows them. Now this slope is barely perceptible. It's about from say 3/4 of an inch to 1.5 or 2 inches per 10 feet of run. The purpose is to allow the water which drops out of solution to coalesce on the bottom and run to a low point where it can be drained out. That's called a water draw. So in this case it's on the perimeter, in this case it's in the center, and in this case on the edge of the tank. Here's a laser scan that shows the actual cone up tank in this case. Red is higher, it's 5.4 inches at this red color, and -5 here, so about 10 inches of difference between this edge and the high point here. Now there's settlement causing this high point, but it's a cone up tank which has tilted, so it's tilted settled in this direction. Here's one that was built as a cone up tank, and it's fairly in fairly good original contour. And again, schematically this shows where the water goes to the edge of the cone up, to the center of a cone down, to the edge of a shovel bottom or single slope tank. Now the shovel bottom, you realize that if a tank is very large, this would have twice the height of, say, a cone up tank, so it's not used when you get over about 100 feet. The cone up and cone down can be used on any size tank. Here are some examples of floating roof tanks. These are new because they're not coated yet. They will be coated. And I'd like to point out that you can see the mold and rust and crud on almost all of the floating roofs. That's because these are subject to direct UV radiation. They're horizontal surfaces, and it appears that they didn't use a good coating. The coating that's used on the shell is subject to much less abuse than the coating that's used on the horizontal surface, where you have direct radiation from the sun as well as ponding water that sits around a good percentage of the year. So this really should be a better immersion service coating, whereas a shell can be a cheaper typical exterior coating system. It's like your car. You can always see that the polish and coating deteriorates on the horizontal surfaces first, and then the side usually stays good, and you can keep polishing that forever. This is a schematic of a fixed roof tank. Here you have the liquid, and above it is the vapor space. There's nothing separating the liquid from the air, so it's vented by openings, and this is just filled with air which moves in and out of the tank as the liquid goes up and down. You can only do this when the liquid is not very volatile. So there are rules from EPA that say that if this liquid is above 11 psi, that's absolute, you have to use a floating roof. So something like diesel could be stored in a tank like this, or lube oil, or some other relatively non-volatile liquid. If you were to store gasoline or crude oil, those have a high vapor pressure, so they have to have a floating roof. This is a picture of the inside of a fixed roof tank. The center column here is made of two channels welded together. You can see that the roof has moved a little bit. It's off center, and these rafters support the roof skin up above of this cone roof or fixed roof tank. I just want to point out that the environment is good for corrosion. You have horizontal shelves where debris, rust, and moisture can collect and start corroding. You have contact between the roof and the rafters so that this forms a good spot for crevice corrosion. But it's hard to get up here to inspect. You can see that this inspector used a bosun's chair and fall protection to access this area. No, this is not a romantic starlit night. This is a view of the storage tank roof with 1,000,000 points of light caused by corrosion coming in from the outside. It's basically paper thin. This is a fixed roof tank, and notice all the waves and undulations. Even though it's called a cone roof and has a shape that's supposed to be conical like this, once there's a little bit of settlement, you get waviness, and then you have the ponding and mold and bacteria growth. So as I said, if you don't want this to corrode, you need a pretty good coating system. Here's a case of packed rust. That is almost like steel. It behaves like steel other than it's brittle. I've actually seen tanks where this has gone all the way through and the operators didn't even know it was completely corroded through. It's just lucky that it didn't break. These areas were small enough that failure didn't happen, but it's hard to detect sometimes, and it only happens, fortunately, rarely. Here's an example of corrosion in the groove welds, and it's a little bit rare or unusual, but the chemistry shouldn't be different enough that you get preferential corrosion here, but obviously in this case you do. Unfortunately, many people don't bother to do the forensic analysis. It would tell them why this is happening, so not too much is known about this groove-like corrosion that occurs at welds. Now, a horizontal groove is not hazardous because there's no axial stresses. If the groove weld was occurring in the vertical weld, that would be a dangerous situation, and that does occur. Another shot of the corrosion which seems to be attacking the weld itself. Here's a riveted tank. There's typically nothing wrong with riveted tanks. The steel's often quite good, but sometimes it isn't. It's a crapshoot, so you really do need to do physicals and chemistry if you're going to work on a tank like this to determine that it's got good weldability characteristics, reasonable toughness, and not too many tramp elements, excessive sulfur or molybdenum that would cause brittleness. But like I say, many of them are quite good, and people seem to have a prejudice against riveted tanks. They have their issues, no doubt. Sometimes there's a leak, or if you try to repair them, you can end up the expansion from welding the head of one rivet just propagates, and you'd end up having to weld all the rivets in a tank. So it's a gamble as to whether or not you can repair a riveted tank. It's truly a gamble. But often it works. I would say more often than not, and it's well worth the money saved. I'll just point out that this dirt on top of the chime is poor practice from a corrosion perspective, because the dirt retains the moisture and is ideal for corrosion to take place. Here's a schematic of the floating roof. It's just a cover that is floating on the liquid surface, so it rides up and down with the oil level. Its purpose is to cut down on evaporation for those volatile liquids. In practice, there are double-deck floating roofs and annular pontoon. So the annular pontoon is just a box-type ring that goes around and supports this deck, which is just a thin membrane, 3/16" steel, that blots out the surface to reduce evaporation. At the perimeter, you have a seal that minimizes the emissions coming out of this annular gap. I'll show you detailed pictures of that in a minute. Because the top is open to the atmosphere, you have to have a drain to drain off the rainwater that occurs. Here's a picture showing the various compartments. You can see the cover plate, radial seams, and then here are legs that support the roof when it lands, and then this is an access compartment. Now the pontoon compartments are subject to leaks from the underside or even rainwater corrosion holes through the top. In any case, you want to ensure that these pontoons have integrity because this is what keeps the floating roof from sinking. I mentioned that the dome is identical to the steel cone in terms of functionality. It keeps the wind and the weather out of the tank. But there are differences. One of them is that the cone typically, when you get over 50, 60 feet in diameter, has to have more than just a center column. It may have to have rows or banks of additional support columns. A geodesic dome of any tank size can be free span. It doesn't need to have any columns. So here's a picture of the geodesic dome from the inside. It's supported by this reticulated aluminum structure covered by aluminum foil. And in this case, on an internal floating roof, they're using an aluminum skin and pontoon type floating roof. Perspective drawing of a tank, quite a good one. It shows the basic components. This wind girder at the top is to stiffen the shell from movement from the wind. We have an access ladder. This is called a rolling roof ladder. It rides on a track, a couple of angle irons that support this rolling roof ladder, and then the membrane of the deck, or the deck of the floating roof, in the pontoon sections, and these legs support the floating roof. In this case, there's a pipe drain. It has articulated joints that allow it to move up and down with the floating roof, and its function is to carry the rainwater out to a valve outside the tank. Here's a schematic of an annular pontoon floating roof tank. These pontoons are vapor and liquid tight, so if you get a leak in one, it won't propagate or cascade over to the others, and that way API has rules that says you have to be able to have two adjacent punctured pontoons plus the center deck punctured, usually from corrosion, without the roof sinking. Now, it's a big deal not to sink the roof because once it sinks, you have a grave fire hazard on your hands, and people could die because of the firefighting exercise that may have to ensue. Here's a schematic that shows the annular pontoon floating roof here versus a double deck, which is essentially two layers over the entire surface that have bulkheads as well. This type of roof is the most robust against sinking. The annular pontoon is kind of a balance between cost and robustness. Now, if you're using an internal floating roof tank, which is a tank that has a fixed roof or a cover, a dome, there are different rules that are covered in API 650 Annex H. These roofs can be aluminum, whereas the external roofs have to be steel construction, usually the annular pontoon or the double deck. For the internal floating roofs, you can use steel, but you can also use aluminum. In this case, this is an aluminum foil attached to these aluminum pipes, and here there's a vapor space under it. These are the legs that support the floating roof when it's landed. There are two positions. One covers normal operation, where you want the floating roof to go down as low as possible so that it maximizes the volume of the tank. But when you're going to work on it, you don't want to be cleaning the tank on your hands and knees, so you pin the roof leg high so that the floating roof is high up in the air so you can stand up straight and mop out and squeegee out the tank. The legs usually have landing pads. These are 1/4-inch steel plates that are rectangular or square or round that help reduce the pounding of these legs on the bottom and eventual corrosion and hole through from abrasion. Another picture of a floating roof. You can see that it spans over here and is able to articulate so that it can get you down onto the floating roof, whether it's in any position from low leg up to high liquid level. Now, this is a picture of a floating roof, an annular pontoon. You can see the pontoon section here. This is the deck, and the seal is way out here. I'll point out that these sheets are probably 10 feet by 40 or 8 by 40, probably 8 by 40 feet long. You can see the plates. But notice that every seam is corroding away, and this is because it's hard to get good coatings and coating protection on welded seams. If you really wanted to do this to prevent corrosion, you might use stripe painting, which is to paint it twice. You might grind the welds, but all that's too costly for floating roofs. So typically this is what they look like after a few years in service, where the corrosion is starting. Also, if you're using a zinc-based primer, it's not going to be very effective because the zinc gets quickly used up if it's in an aqueous, wet environment. So zinc is better on things like galvanized fence posts, where you just occasionally have moisture where it will protect the fence post. But if it's in moisture for a long period of time, it'll get used up within a year or two. Now, the underside of a floating roof is a different corrosion environment. On the top side, these plates are lapped and they're seal welded with a fillet weld, but underneath they're typically not welded. So this is an ideal place for crevice corrosion. I've seen these seams that are lapped like this just get pried apart, where this bottom piece will be pushed down because the corrosion product has built up so much pressure, it's just forced this downward. These are access hatches to the pontoons. Rather than go inside these pontoons, it can be done, but it's a confined space entry. Most people are going to use atmospheric testing to detect whether there's hydrocarbons inside here, and hence a potential leak. It's important not to have flammable gases in here. There have been some notable incidents where lightning struck nearby this manway and caused the pontoon to explode, and the whole roof blew out of the tank and the deck got sunken. So there are a number of incidents caused by that. Here is a seal. This is not used too much anymore. This is a bag seal or a foam log seal. It's basically foam filled inside of a tubular membrane, but you can imagine that the sharp edges of the welds shreds this thing pretty quickly, and then it just fills with fuel and becomes a hazardous waste. So it's no wonder that this has fallen out of favor. Here's the skin and pontoon that we saw earlier in one of the photos. A more common seal, especially for external floating roof tanks where you have a lot of buoyancy and support by the steel roof, is a shoe seal. This strip of metal, it's kind of shown here going down to here, is the shoe. It's pushed outward by this spring mechanism against the shell. Its purpose is to center the roof, provide some radial force to center the roof, and also to reduce any liquid and vapors from getting through it. There's an additional membrane here that covers the top, so while this space may be saturated with organic vapors, it does a pretty good job at eliminating vapor emissions. There are some, however, and that can be calculated by looking at other API documents. You can see that there are a lot of components, pins and springs and what have you. If this is going to be used for any length of time, to 10 years or over, I would recommend stainless steel. The cheaper systems are galvanized sheet metal and so forth, and these components start rotting out within 5 to 10 years. So if you have a service, even if it's non-corrosive, this will not last very long. If it's corrosive, you certainly would not want to use galvanized steel. Here's a view looking at the shoe seal. This is the sheet metal I talked about. Here's a pusher spring. This line here is the vertical, and this is a horizontal edge of the outside of the pontoon. And then, of course, this is a seal fabric. So it was filled with liquid. The liquid would be 6 inches up above this bottom and going across, and that vapor would be stopped by this vapor fabric. I mentioned the rainwater drainage. This hose is just like a garden hose, except it could be 6 to 8 inches in diameter, and you could have more than one. So it's usually coiled around and goes outside the tank to a valve like this. It has to be managed by operating. This is an aluminum Annex H, or internal floating roof. These plates are bolted to lightweight aluminum framing structure. You can see here in this case they got some oil on it. Aluminum can work well, and it has its place, but when it doesn't work, it fails pretty dramatically, as in this case. The problem with aluminum as a material is that it's a little bit unpredictable in liquid service. So the aluminum frying pan that you use is, or maybe you don't, most people have gotten away from that, but The oxide layer, because aluminum is exposed to air, it is very good at inhibiting corrosion, but when you put it in a liquid surface, the oxide layer can easily be destroyed, and so it's quirky in terms of corrosion and has to be carefully selected by an experienced metallurgist if you're considering aluminum. This is a steel pan, a bulkheaded pan roof. It doesn't have the covers, it's just an open top. And again, this is a corrosive environment because it's a low point. There are cases where this roof has sunk because leakage from a geodesic dome, the dripping has caused corrosion holes, and then these pontoons filled up with liquid. Here's an oil and gas journal article that Earl Crochet and George Morovich and I wrote to talk about some of the advantages and disadvantages of cone roofs versus geodesic domes. So you can look this article up. One of the main points I recall is that we were talking about trying to inspect under the columns. You can imagine this is holding up a lot of weight. Plate is not attached to the tank bottom, so a crevice corrosion can be going on. So even if you checked the bottom and saw no leaks, there could be a leak under one of these columns. Some people jack them up to try to find it, others don't do that. Here's a picture of one of these columns. This plate has to be free to move up and down in these guides, a couple of pieces of angle, because all tanks settle, and that settlement, when it happens, you don't want that to pull down or push up on the roof, so it has to be free to move like this, and therefore the area underneath this plate is part of the steel bottom and it can corrode out. The three main zones of corrosion in a tank are the bottom, where you have water, as I mentioned. Product itself can be corrosive. Most fuels like gasoline and lube oil are very uncorrosive. You're talking less than 1 mil per year. But something like aviation gasoline is quite corrosive. And of course, in the chemical industry, there are many different types of organic chemicals, some of which are very corrosive. You can get interface corrosion, product side corrosion here, aqueous water phase corrosion down the bottom. And then in the vapor space, you've got moisture, saturated air, and water condensing out, and you get corrosion in the various components up in the vapor space. In some sour services, especially in producing facilities, the hydrogen sulfide forms sulfurous acid when it's in contact with the water. So it's a dilute acid, but it's very corrosive. Sometimes the corrosion is so bad in the vapor space that operators will put the rafters on the outside like this so that they have a smooth surface that can be coated and not corrode away in a very short period of time. This is an important slide. It shows that the environment on the soil side of the bottom, or the underside or bottom side of a tank bottom, is highly variable. So in the winter you have a lot of water on the outside, and it would look like this. If this is the outside and this is the inside, it'll be wetter towards the outside. But in the summer, when things are drying up, it'll be less moisture on the outside and more on the inside. The same thing is going on with all the other basic corrosion environmental properties like oxygen concentration and dissolved salts. So you can see that at some point in here, you're likely to have conditions that are just right for corrosion to be maximized. In fact, many tanks, not all, but a good percentage of tanks, probably in the order of 20%, have a definite corrosion pattern that occurs like this, within 10 to 15, 20 feet of the perimeter, because of some combination of these variables that is just right for maximizing corrosion. Now this just shows soil-side corrosion. You have to have 4 things for corrosion to occur: an anode, where you're losing steel, an electrolyte or a current path flow so that the ions can travel from the anode to the cathode, and then an electrical circuit from the cathode back to the anode. This is a schematic of a double bottom tank. These are fairly common. When this old original bottom corrodes out, many operators put in a double bottom, and this is how you would do it. This becomes a new bottom. This distance is only about 4 or 5 inches. This can be filled with a spacer material. It can be sand typically, and sometimes concrete. I worked on a facility where the original bottoms lasted 20 to 30 years, and when they put the new bottoms in, the tank only lasted 10 years. Why is that? Well, new steel is anodic to old steel. It's been more freshly put through the meat grinder, so to speak, in the manufacturing with the rollers and squeezing out the steel crystals, and they're more active, so it is anodic to the older steel. Because they didn't insulate between the anode and the cathode, this became the anode and it corroded out in about 10 years, like I say. The solution is to put a dielectric or insulating material on the bottom, something like a polyethylene. It's ideal because it's cheap. It guarantees that if you do have a release from the new steel bottom, it's not going to go through into the old bottom and into the ground. It'll be intercepted by the release prevention barrier, and it also primarily stops that accelerated corrosion. In addition, if you have a sand bottom, you're going to want to probably put some kind of ribbon or a sacrificial or impressed current system to drive current to the new bottom so it doesn't corrode. Unfortunately, in these systems, often what happens is the designer is basing the current demand on clean, new, non-conductive sand, but the first time this gets flooded and wet with salts or floodwaters, the design of the current system is inadequate and tank corrodes away, so you see that quite often. Here's a tank bottom, looks nice, like the bottom of a Teflon frying pan. Here's a bottom plate. This is a zinc anode, and it's attached to the bottom. The only place this is used typically is in crude oil tanks, because crude oil has brine in the bottom. It's a salty, very corrosive water, and you have to coat the bottom and up the sides 2 or 3 feet, like we saw in that one of those first pictures. But no coating is perfect, and so by adding the sacrificial zinc anode, what you're doing is protecting the coating from failing because of small discontinuities and holes and defects in the coating system. And so the current requirements aren't very high, and this anode can last 20 years. If you had no coating in here, you'd have to space these every couple of feet and they wouldn't last a year. Here's a schematic of a double bottom. We talked about this. Here's sand and some cathodic protection. Usually there's a pipe that is allowing you to drain out a release. These should not be closed because then you defeat the purpose of the release detection. But also, I've seen tanks that had these closed and pressure has built up inside here and caused this bottom to bow up when the tank was emptied of liquid and the air that was compressed in there pushed up the bottom. So there's no reason to close those off. That's a bad practice. The other thing is I recommend not seal welding this because it's almost impossible to do a good job welding it since it's in a bad position for welding. This tank were to suffer uplift from seismic or overpressure or whatever, a crack in that bottom lousy weld could propagate into the tank bottom or shell and cause a catastrophic release. This just shows a picture of a sump and how it's installed. Sumps are another place where you want to thicken the steel. Usually these are twice as thick as the bottom, a ½ inch instead of a ¼ inch, because you're getting corrosion from both sides and all the crud in the water. This is a low point. It's like the garbage disposal in your sink. It's picking up all the crud, and it's a terrible environment in terms of corrosion. Here's a picture of making a double bottom. What you do is get a torch and slot this. Dogs are welded on here to keep the bottom separated, and then the new plates are slid in and you have a new tank bottom. A picture of a tank sump, and like I said, it's the low point where all the water and the crud accumulates. We have here the concrete that is under a new bottom. So if the spacer material is concrete, a lot of people will slot the concrete with roughly 2 inch by 2 inch grooves. Here it says saw cut 3/4 inch deep by 1.5 wide grooves. Some people report that there's excessive corrosion as a result of that. And the purpose of these is to detect a leak. If I had a leak here, it would come out of this radial. If I had a leak on this side, it would come out of that one. And similarly here, if I had a leak in this one, I'd know roughly where it's coming from. But I see that as kind of pointless, because if you have a leak anywhere that it's coming out, that tank needs to come out of service now, and you need to open up and clean the tank, gas free it, and find out what happened. So I think this is one of these old wives' tales. Now, a leak can still get out even if there is no slots or like this, because the bottom is lapped, so it can always get out through the gap caused by the lap construction. If you have a sump, which in a concrete foundation or slab foundation, you want to leave enough room around it so that the sump, due to differential thermal expansion or movement from settlement, doesn't shear that sump off of the bottom and you end up with a catastrophic release. All tank bottoms settle, so you're going to get low points where water can pool. There's no getting around that. So coating the bottom is a good general solution for that. You also get pockets and bulges like this that do the same thing. They form water retaining little pools in the tank bottom. Here's a picture of the dog I described that holds the shell apart while you put this plate in and weld it up and form a new bottom. This is just a sampling of the way some cathodic protection is done. Here's a permanently installed reference electrode under the tank bottom. In this case, we have a perforated PVC pipe. The test electrode can be inserted into that pipe, and the perforations allow for the environment to contact the reference electrode. If you have nearby DOT pipelines, you want to watch out for straight current corrosion. If your tank is in between the anodes of the pipeline system and the pipeline, for example, the current goes right through the tank, and where it leaves, you have corrosion. You have an anode here. This is a galvanic series type corrosion where you have the steel, which is anodic to stainless or copper pipe, corroding away. Corrosion rates, like any chemical reaction, increase about by a factor of 2 for every 10 degrees C increase. But here's an example of how you heat up a tank like crude oil to keep it warm. These are serpentine steam coils that are typically 2 inches in diameter with 150 psi steam on the inside. Notice this tank had concerns about corrosion, so it's well coated. Systems of insulation for tanks are very complex. You can see that there are many layers and lots of little hardware and elements. The key thing is, if you don't do a good job, you're almost better off not insulating the tank, because any moisture that gets in here will cause corrosion, and it's hard to detect it. It's got its own name, corrosion under insulation, or CUI. It's difficult to detect and very expensive to repair. Another problem with these insulation systems, if you do get moisture, you should be making sure that this insulating medium does not release salts like chlorides or other corrosive chemicals when it gets wet, which is fairly typical, and cause excessive corrosion. And zinc primers usually are not going to work because, like I said, the zinc gets quickly eaten up by the moisture. So as soon as it's gone, the salts that are leaching out of this insulation will start pitting the tank severely. In insulated systems where it's careful to maintain the temperature here, if this gets wet, this heat transfer line will, this point here, even though the outside and the inside temperatures are the same, the slope of this line can go up and down, and the surface temperature will change. So for example, in a cold tank, the line would be going up instead of down. But in a cold tank, if this starts sweating because you can't maintain the temperature properly above the sweating or condensation point, you'll get aggressive corrosion. And that will happen if your insulation gets wet and is no longer maintaining the proper temperature. What I was talking about, this point, this temperature of the steel will move up and down to the wrong regions, and you'll get accelerated corrosion. Tanks are big, so these insulation systems have to have straps for thermal expansion. The insulation has to be able to move with the tank. It's a fairly complex system. So if you're going to insulate, you should be studying these systems. Some are better than the others, and they are all somewhat complicated, and every one of them, it's very difficult to keep all the water out. Here's just a picture of a sacrificial anode cathodic protection system. Usually a hole is bored in the ground and proper engineered backfill or coke is used, and then the mixed metal oxides or carbon zinc based anodes are put in, and it protects the bottom. This is only going to work on a fairly small diameter tank though, because you have the IR drop, the resistance of the ground. Sometimes liners are used in secondary containment, as in this case. You would have to put your cathodic protection between the liner and the tank bottom. If it were down here, the current would be stopped by this liner and you would have no effective cathodic protection. So this is the conclusion of part 1. We'll see you on part 2. Thank you.